So where we ended off last class is we just started the stereochemistry portion of the class, and so this is essentially the field of chemistry, which deals with basically three-dimensional arrangements of atoms, where the connectivity of the various atoms is the same, but the three-dimensional arrangement's different. And this is basically has very profound effects in biology and biochemistry and med chem and all that type of stuff. So it's relatively important. Now, before we do that, let's just do a couple of practice questions from last class. We just finished the section on conformational analysis using Newman projections, in addition to chairs and boats, or chairs, sorry. Cyclohexane rings with various substituents. So the first couple of questions are just about the analysis of these types of structures. So which chair is the more stable conformation? So to solve a problem like this, the destabilizing interactions for chair conformations are steric interactions, which is very similar to a gauche interaction of a Newman projection. And it manifests itself as what we call 1,3 diaxial strain. So anytime you've got an axial substituent, it is going to interact with the protons that are also, or other groups that are axial. So this axial methyl group will interact with the proton here and the proton here. So there's 1,3 diaxial interaction. And the chair on the right, we've got an axial methyl group here, and we've got an axial methyl group here. So this one will be interacting with the proton on this carbon and the proton on this carbon, whereas this will be interacting with the proton, which would be here, and the proton, which would be here. So B has got 2 of these destabilizing interactions, whereas A has only got 1. And so, let's move this little screen here, up there. A would be the correct response. It has only got 1 destabilizing interaction, so it should be the most stable chair. Good. Okay, let's move on to the next one. Start question. So here we've got a different chair with different groups on it. Okay, so let's see, spotlight. So with all the rules I just mentioned, there's always exceptions to these rules, and the big exception to when it comes to chair conformations and substituents, this tert-butyl group is so big and so, like, in the 1,3, when the axial position, it is so destabilizing. This equilibrium is going to shift to B to put this tert-butyl group equatorial. The only time where you find a tert-butyl group axial tends to be when there's another tert-butyl group equatorial. So it's helpless. In one conformation, it'll be axial regardless. So this large group, the energy associated, the steric energy associated with the interactions with these protons over here is so large that it's going to ring flip and form B. Even though in conformer B, we've got 2 axial methyl groups. The energy associated with these 2 is not enough to overcome this large group being axial. So whenever you see a tert-butyl group, its preference is overwhelmingly to be equatorial. So B is the correct answer for this one. So typically the value, the destabilizing energy values they vary as the group gets larger and larger. So, but for most of the stuff that we're doing in this class, you can just count the number of axial substituents on each conformer, and the one with the least would be the lowest energy. The big exception, of course, is the tert-butyl group. All right. And the value for these energies is called the A value. So you can actually look them up if you're ever that curious to see what groups, how large their destabilizing energies are. Alkyl groups tend to be more destabilizing than, say, a hydroxyl group or something like this, mainly because on an alkyl group, you've got protons bonded to the various carbons. So this methyl group's got 3 protons bonded to it. This methyl group's got 3 protons bonded to it. So they're larger, they take up more space. Okay, let's see, let's move on. Let's close this. So I think we got to around here when we were talking about that certain molecules are like our hands. So they are mirror images of one another, but yet you can't superimpose them on themselves. So if you put, like your hands, when you put them together, basically the palm, there's a mirror between your palms, but if you flip them over and put one hand on the top of the palm of one hand on the palm on the back of a hand, the fingers don't line up anymore. So that's what we mean by mirror images, but they're not superimposable. So molecules which have this, so whenever you have, there'll always be 2 molecules which have this characteristic with one another, and they're called enantiomers. So they're a specific type of stereoisomer that are mirror images of one another, but they're non-superimposable. And enantio comes from the Greek for opposite. So one class of stereoisomer will be enantiomers. And an example we gave last class was basically lactic acid. So we've got a carboxylic acid here. This carbon is bonded to 4 different types of groups: proton, methyl group, hydroxyl group, carboxylic acid. So what we're going to see is that the main source of this of handedness for organic molecules is a carbon bonded to 4 different substituents. So there's 2 different forms of lactic acid, what we would call plus lactic acid and minus lactic acid. And we'll figure out what this means in a second, but they're not superimposable on one another. So if we rotate, and I actually went to work yesterday and I got my model set and I left it on my desk so when I left I could bring it with me, and of course I totally forgot it. But if we rotate this bond through this carbon and this hydrogen, so we can move this carboxylic acid to the right-hand side, so it's going to be in the same position as this. The act of rotating this 180 degrees means that this methyl group, which is out front, is going to move all the way to the back. The hydroxyl group, which is the back, is going to move all the way to the front. And then if we try to superimpose this on the other lactic acid, this group, this carboxylic acid, the carbon and the hydrogen, carboxylic acid, carbon and hydrogen, they're all in the plane of the board. So they all line up perfect, but the big difference is we've got a hydroxyl group pointing towards us in the minus lactic acid, whereas in the plus, we've got the methyl group pointing towards us. So they've got the same atoms, they've got the same connectivity, but their three-dimensional spatial arrangement is different. So these would be mirror images, non-superimposable, i.e. enantiomers. So molecules that are non-superimposable with their mirror images are enantiomers, which we just said. And there's another word we are used for these types of molecules, and that is that they are chiral. And that is Greek for hand. So just where we started with, so some molecules are going to be like our hands, and they're going to be chiral, and there's other molecules that will not be like our hands, and we will call them achiral. So there's a whole host of molecules that are achiral. So for example, H2, N2, O2, all of these molecules, there's, if you were to take a mirror image of it, it would be completely superimposable on itself. So those would be achiral molecules. So one of the things we're going to learn how to do is to determine if a molecule is chiral or not. So as I said before, the most common source of chirality in organic chemistry is to have a carbon with 4 different substituents. Now, the technical, that's the easiest way to determine it. There's the technical version for determining chirality is whether or not the molecule possesses a plane of symmetry. So if the molecule possesses a plane of symmetry, it is achiral. But if the molecule doesn't have a plane of symmetry, then it would be chiral. So planes of symmetry. Now this is where visualizing things in 3 dimensions can be problematic. So for example, let me draw something here. Draw something. So if we just have a molecule which is a straight zigzag, so we would call this butane. And I was to ask everybody, does this molecule have a plane of symmetry? The answer would be, no, remember, I haven't even drawn the protons on this. But does this molecule have a plane of symmetry? All right, now I'm going to draw the protons on it in a specific conformation, and you can maybe tell me if you can see if there is a plane of symmetry or not. Because remember, each carbon is tetrahedral in this case. Now, does this drawing help determine whether or not this molecule's got a plane of symmetry or not? If I draw it like that, when I add the protons to it.
I mean, I think it still does.
That it's got a plane of symmetry?
Yeah.
Yeah, you're right. It does have a plane of symmetry. So there is, in fact, you can rotate the bonds in a couple ways and there'll be multiple planes of symmetry. But the easiest one, at least for me to see, is that, okay, so this proton, this carbon, this carbon, this carbon, this carbon, and this proton, the way we've drawn this, they're all in the plane of the blackboard, right? And so the plane of symmetry would bisect it would cut all of these molecules right in half, right? So it's halfway between each atom. And then this proton here is reflected in the mirror by this proton. This proton is, so when we're talking about a plane of symmetry, it's going to have, it's almost like a mirror dividing the molecule in half. And if things reflect one another, then you would say it's got a plane. So this proton's reflected by this one, this proton's reflected by this one, and then all the remaining protons are divided in half. So butane has got a plane of symmetry, and so it would be achiral. And the other thing which is interesting is that if you look at each carbon, you can say to yourself, does this carbon here have 4 different substituents on it? Well, on one side, it's got a methyl group, and on one side, it's got a CH2CH3, which is an ethyl group. So that's 2, but this is a proton, and this is a proton. So it's got a grand total of 3 different substituents. And if it's got 3 different substituents, that's not 4, right? We need 4 different substituents. We can do a similar analysis on every other carbon, and the greatest number, like this one's got 3 different substituents as well. This one's only got 2 different substituents. It's got protons plus this long chain, which would be a propyl group. So the easiest way to recognize if a molecule is chiral or not is to look at the various carbons and determine, does any of these carbons have 4 different substituents? But the best, there's examples, because you can find examples where you do have carbons with 4 different substituents, but it is still achiral, and we're going to get to that a bit later on. But so the proper definition really is if it contains, if it's chiral, it will not contain a plane of symmetry. So if it's got a plane of symmetry, it'll be an achiral molecule. So let's see here. What's another little simple example? Now, let's just change one thing on butane here. Let's put a hydroxyl group right here. And so if we put on let's draw the proton here just to help everybody out, and we can draw all of the other protons. So now we've got a hydroxyl group on the second carbon in this chain. The plane of symmetry that existed before, where you bisect this proton, this carbon, this carbon, this carbon, and this carbon, and this proton, it no longer exists because this H is reflected by a hydroxyl group, which is different than the H, right? So this molecule here doesn't contain that same plane of symmetry. So this molecule should be chiral. And if we look at this carbon here, it now has 4 different substituents. It's got a ethyl group, an ethyl group, a proton, and a hydroxyl group. So that's 4. And so this guy here is indeed a chiral molecule, and it will have a mirror image that is non-superimposable. It's an enantiomeric pair, so to speak. And the enantiomer of this molecule will be the same 4-carbon chain, but on the second carbon, instead of the proton being pointing towards us, it's going to be pointed away. That's just a heads up of what's to come. Okay, so let's see if people can, everyone can see. Oh no, let's clear my drawings. So here's an example which fits sort of nicely with what we just talked about. So we've got propionic acid and lactic acid. So the previous example before. So propionic acid, the only difference between propionic acid and lactic acid is this hydroxyl group on this carbon. So on propionic acid, it only has 3 substituents, right? 1, 2, and then these 2 protons are the same. So it's achiral. Lactic acid, there's 4 different groups. But the plane here in this molecule is it bisects this hydrogen, it bisects the carbon, it bisects the carbon, it bisects the carbon and the oxygen and the oxygen and this proton. So all of these things are in a perfect zigzag, right? They're all in the same plane, all zigzagged. And then the two groups that reflect one another are above. This H is above the plane, this H is below it, and they reflect each other perfectly, as do those. But once you add this hydroxyl group here, it's now reflected by a proton, and that destroys this entire plane. So that's how a plane of symmetry would work. If you really like visualizing stuff like planes of symmetry, and there's a whole bunch of different sort of symmetry operators, you should definitely take the group theory class with Dr. Yan next term, because there's a whole bunch, in organic chemistry, there's a whole bunch of really fun sort of, particularly when you're dealing with transition metals, there's a whole bunch of really fun things. And it relates back to math. That's why a lot of math students like group theory, the group theory class. But anyway, there's no math in that class, but there's a whole bunch of symmetry operations for it. So that's kind of fun. Anyway, this is what I wanted to get to, our question. So I've got 3 molecules here. I'll actually add some extra time because this might take a little while. I'm just interested to see if you can tell me if these molecules would have a plane of symmetry or not. And I haven't drawn, well, with the exception of molecule A here, where I've drawn some wedges, and I haven't drawn any wedges or dashed lines in any of these. Because remember, if something could be a chiral, there'll be 2 different enantiomers of it, at least. So just take a look at them and see if you can recognize where the plane of symmetry is, or if it doesn't exist at all. Let's add some time. Okay, let's see what everybody said here. So molecule A, B, and C, the responses were that A has a plane of symmetry, B has a plane of symmetry, but C does not. And the highest number of totals was with C, and the lowest was with B. Okay, let's show what's correct or not. And this is, all 3 of these are right. So C does not, A and B both do. Okay, so let's look at these. So it's hard to, I'll try to draw, I'm going to draw this, I'm going to draw this A as a chair because it's easier to see it, I think, as a chair. But the plane of symmetry basically bisects right down here, and then I'd have to change the way I draw this Turk beetle group to make it look good. So if this is our chair, the plane bisects carbon, all the carbons with the little dots and this oxygen. So the plane goes right down the middle of the chair, as sort of as I've drawn it here. This methyl group reflects that methyl group. These carbons reflect these carbons. These carbons reflect these carbons. So that's the plane of symmetry with regard to molecule A. Hopefully everyone can see that. But if we look at this molecule, you'll notice that there's no carbon which has got 4 different substituents. The one which is probably the biggest question mark is this carbon here. It has got a Turk butyl on one side. It's got a hydrogen, which we haven't drawn. So those are 2. 1, 2. And then the rest of this ring is exactly the same no matter which direction you go. So CH2 bonded to a CH2, and then if you move over here, CH2 bonded to a ketone. So this part, the rest of this is all the same. So it's only got 3 different substituents. B is probably B had the lowest response rate with regard to lowest. Wait a second. How do I? Let's turn that little thing off here. So B, only 21 people answered yes to B. So B was the one which was probably the hardest to see. So let's draw this one. Hopefully I can draw it in a way which we'll see. Okay, so this carbon here, we're going to draw this carbon here first. Carbon, OH, H. So I've drawn the proton, which is attached to the carbon here, and then the hydroxyl group. Then this is tetrahedral, so all 4 of these atoms are in the same plane of the board. Now we got to draw these 2 substituents. So one is going to be pointing towards us, and this is a CH2, CH3, which is an ethyl group. And on the other side, we've got a CH2, CH3, which is also an ethyl group. And so the plane would bisect the hydrogen, bisect the carbon, bisect the oxygen, bisect the hydrogen, and then these 2 guys, which are the same, reflect one another. So this B does have a plane. Now C, everyone seemed to get, highest degree of confidence was on this one. And so that's right. So this molecule here, this carbon has got 4 different substituents. It's got a methyl group, it's got a propyl group, it's got a hydrogen, and it's got a hydroxyl group. And if we were to draw it in a similar fashion as to this guy here, we would have methyl, OH. Oh, actually, let's erase this. Hydrogen. We would have a methyl group on one side and a propyl group on the other. So the plane, there is no plane of symmetry here because this methyl group is reflected by a propyl when they're not the same. So this carbon here is, this molecule here is chiral.
I have a question regarding that.
Okay.
Since the carbon chain can rotate freely, is it chiral? Because couldn't it rotate to be a mirror image?
It can't rotate to be a mirror image because there's 4.
1, 2, 3, 4, 5. It's substituted on the second carbon. So if this were to flip, it would be on the opposite second carbon. Is why I ask.
I wish I could see what. what you mean.
Okay, so like these, and then you flip it. Or if you rotate it. My camera's on, did you see?
Yeah, okay, so I saw what you're doing.
Like the 2 points would rotate. And then this would be in this point from this point, right? I'm just
do you have a model?
Well, I've got a chain, but
Right. So, okay, so let me
here, I'll try. I'll use the model. Okay.
It's true that these bonds can all rotate, and that you could draw a conformation in which there isn't that mirror plane. But the question is, you could draw, in molecule B, you could have it so the carbon's here, H is here, OH. You could have it drawn so that it's CH2 and then the CH3 is pointing over in this direction, and that the CH2 and then the CH3 is over here. So it doesn't line up like a mirror, but that's not there are conformations where there isn't a mirror plane, but is there one conformation where there is a mirror plane? And if there is, that's the issue. So because there's a million different, because bonds can rotate at an infinitesimally small degree, angle, you could have potentially an infinite number of conformations where the mirror plane is destroyed. But the problem is that if there's one where there is, that's the kicker.
Okay, so even if it's chiral, even if it doesn't necessarily make a difference to how it can interact?
Right, so you could, all of these bonds here. Okay, so yeah, so you've got, okay, but this one is a chiral molecule, right?
Yes.
The one you've made, right?
Yes, I think so. It's got 5 and it's on the second carbon.
Right. Okay, so how are you going to do that? Okay, so what you're doing is you're rotating the entire molecule.
Yeah, so it doesn't have a plane of symmetry, but I think that it can move freely. So as a result, it's not handed, I guess, although chiral literally means handed.
So
if I were to move this over to a different spot, for example, and then you could rotate it back.
Okay, but we're not allowed to break any of the bonds.
Oh yeah, that's why I'm just saying I'm wondering if it's handed, because if I were to switch where this was, then I could rotate it so it's back to being the same. Even though it's on a plane of symmetry, it doesn't necessarily change. That's why I'm wondering.
Okay, so if you put the hydroxyl group on the second carbon, it's a chiral molecule. If you put it on the first carbon, it's not. And if you put it on the third carbon, it's not. Because if on the end, there would be a plane of symmetry which would bisect the entire molecule. On the third carbon, we've basically got molecule B, where you've got two ethyl, you don't have a carbon which has got 4 different substituents. So
with respect to that carbon, the second carbon, it certainly is chiral, but as the molecule, I'm wondering.
Yes, so this is where we're gonna get to.
We're not there yet.
So the source of chirality for a molecule is going to be, often it's just one carbon which has got 4 different substituents. So the molecule itself, we would say, is chiral, but the source is it could be just one carbon. So the carbon's the source of the chirality, but the molecule itself possesses chirality.
Okay, I think I get it now, because if you look at this group on the end there as separate, it's true that you can't change the position of this one with respect to the methyl group.
Right.
This bond. If you're referring to this area, then yes, okay, I get it. Makes sense. Sorry.
Excellent. Okay. All right, so this little side here is basically saying what I'd said before, that the most common source of chirality is a carbon that is bonded to 4 different groups. Yeah, so this is typically the way which we will determine whether or not a molecule is chiral or not. Looking for a mirror plane can be challenging, but this is usually easy to find. So these carbons that have got 4 different groups are called chiral centers. They're called asymmetric centers. They're called stereogenic centers. Sometimes they're called chiral carbons. All of these names are legitimate. So basically, it's like stereogenic center, chiral center, asymmetric center. All of these are all saying the same thing, that this is a carbon that's bonded to 4 different groups. So chemists like to come up with lots of names to describe the same thing, and often some of the names are quite. I went to there was one conference which a fella got up there and just read some of the experimental protocols that chemists use and the language that they use to describe just some really simple words, and they use the most complex words, which is just, it was comical oh god, it was funny. But anyway, so all of these things mean the same thing. Chiral center is probably the term I'm going to use the most. All right. Okay, so chirality is a property of the entire molecule, but the source of the chirality is basically can be just one carbon. So here we've got a long chain. There's a hydroxyl group, proton, methyl, and then this butyl group. So a carbon bonded to 4 different things. So this will be a chiral center. The second molecule here, there's a plane of symmetry which bisects the hydrogen, oxygen, carbon, the methyl, and this carbon over here. And then these groups and these groups reflect one another. It's easier to see if we draw this as a chair. So the plane bisects hydrogen, the carbon, this carbon, all of these, and this carbon over here. Now, if we suddenly add a ketone to this molecule, like put a ketone right here, now the mirror plane's destroyed because this carbon's got a ketone on it and this carbon doesn't. So, and you can look at this carbon here and it's got 4 different groups, 1, 2, CH2, and then ketone, 4. So this would be a chiral center. And then this is the example we had before, a 5-carbon chain and ethyl group on one side, ethyl group on the other. So it's not a chiral center. But if it was moved over by one like we had, it would be a chiral center and the molecule would be chiral. So chirality is a property of the entire molecule. The source of the chirality is chiral center. There are some very large molecules that don't have chiral centers that are chiral, and it's like some polymers are chiral because the way that they wrap their spiral, and the spirals can be clockwise or counterclockwise. But that's one of the exceptions to the rule for that. All right. Good. Okay, so what is next? Okay, so now let's talk about the enantiomers. So you're always going to have a pair. There's going to be the left hand and the right hand. They've got basically the same physical properties. So enantiomers will have the same melting point. They'll have the same boiling point. They'll have the same density. They will have the same solubilities in achiral solvents. So they'll have the same solubilities in molecules that are achiral. They'll have different solubilities, of course, in molecules that happen to be chiral. The main difference about what enantiomers do, the main physical property that they have, is their ability to rotate plane polarized light. So each enantiomer is actually going to rotate plane polarized light by the same amount, but in opposite directions. So way back at the start of this class, we talked about plus lactic acid and minus lactic acid. And what that plus and that minus means is that one is rotating plane polarized light clockwise and one is rotating it counterclockwise. But what the hell do we mean by plane polarized light? So this is an ugly diagram, but if we had so remember, electromagnetic radiation, light has got, basically it's got two components to it, but it travels as a wave. And so let's see if I got a little drawing here. So most of the time when you see light being drawn, you'll see this wave like drawn like a sine wave. And we draw it in that perspective, like up and down, because it's the easiest one to draw. But if we were to look at this head on, like a Newman projection, some of the light would be traveling in this way. Some of the light would be traveling this way. Actually, light's got, it's got two components, but some would be traveling like this. Some would be traveling like this. Some would be traveling like this. It would basically cover all of the directions of the, like of a, would be in every direction. But if you put it through a filter, the light which actually makes it through is only pointing up and down. So it filters out the rest, which isn't like this. Then as it's traveling through your solution of chiral molecules, this light can be rotated clockwise, or the light can be rotated counterclockwise from its starting position. That's basically what, is it going to go to 1 o'clock or 2 o'clock or 3 o'clock, or is it going to go to 11 o'clock, 10 o'clock, or 9 o'clock? That's what's basically going on. So if you put this plane polarized light through a solution of achiral molecules, nothing happens. It stays exactly where it was. But if you pass it through a solution of chiral molecules, it's going to be rotated one direction or the other. And so now I have to read the history of this, why they decided to try this experiment, but someone did and came to this conclusion. So because chiral molecules can rotate plane polarized light, they call these molecules optically active, because that was the only, way back in the day, this was the only way to determine if something was chiral or not. Was it optically active? Does it rotate plane polarized light? Since then, there's other things that we can do which to tell us if it's chiral or not. That's outside the scope of the course. But historically, this is what the this is how this was determined. So if you're lucky enough to take phys chem, you get to use a polarimeter which will rotate plane polarized light. So that's kind of fun. I remember when I was an undergrad, there was an experiment where we did a hydrolysis of a sugar. And of course, sugars are chiral. And during the hydrolysis process, you could see by the rate of the reaction by how the plane polarized light was changing from its starting point, which was kind of fun. Anyway, so chiral molecules are another term you would hear is optically active. So they can rotate plane polarized light. So one enantiomer will rotate it one direction, the other enantiomer will rotate it exactly the opposite direction. So dextrorotatory or levorotatory. So minus or plus. So each pair will have its own, each There will be an enantiomer. Its pair, one will be plus, one will be minus. So there are lots of natural occurring substances that are chiral. Morphine is one, and if you put it in a polarimeter, it is minus. Sucrose is another. You put it in the polarimeter, it is plus. So you can make the enantiomer of morphine if you wanted to, and it would rotate plane polarized light in the opposite direction, so it would be positive. And you, if you wanted to, you could make the enantiomer of sucrose, and you could, it would be optically active, but it would be, it would rotate plane polarized light in exactly the opposite direction. Fun. Okay, so if you ever look at a bottle of something and it says minus or plus, what it's telling you is that, yes, this is this compound you're about to use is chiral, and this happens to be the plus enantiomer or the minus enantiomer. If you ever look at a bottle of something and it's got a plus and a minus underneath, that means it's a mixture of both enantiomers. Sometimes it's cheaper to buy a mixture of both, so that's why you would have it. So that's basically what you would see if you ever see that on a bottle. Questions at all? Okay. Now, this is just to, there is a, back in the day, like when organic chemistry, when it was in its infancy, optical activity was one of the few ways to determine whether or not something was chiral or not. And so there's a standardized way of measuring these, the optical activity. And so this is called an alpha D, which is what this little thing down here is, alpha D. So D is the D line of sodium, and it's specific to a certain value. So in your polarimeter, when you're measuring this, there's going to be an observed rotation in degrees. And then they standardized what the path length would be, which was in decameters. And then there was a concentration. You'd have to have your concentration in grams per milliliter. And so this is how your alpha D is calculated. So you needed your concentration to be in grams per milliliters. And the path length was the same for all of these machines. So the concentration is important because the greater the number of chiral molecules in your solution, the greater the rotation. So if the concentration was low, the amount of the rotation would be less. But if you were to have the same concentration of two different enantiomers and put it through and measure the specific rotation, those values will be exactly opposite. So one would be plus 2.5, the other one will be minus 2.5. But if you ever hear the term alpha D, this is the specific rotation, and this is a way of measuring optical activity. All right, now, this is a good point here. Let's see here. So let's pretend that we've got this molecule, and we've got its enantiomer, which would be this molecule. So these are enantiomers. So a lot of the stuff that we do is we do stuff in the lab and we visualize stuff on paper. So these are the two butanol. And so the carbon where we've got the wedge or the dash, that carbon's got 4 different substituents. Methyl group, the proton we haven't drawn, the hydroxyl group, and the ethyl group. So these two compounds are enantiomers. And the way that we've drawn this is that what chemists have come up with is a methodology of determining the configuration at the chiral carbon. So what we're going to do next is learn how to assign a configuration at a chiral center. And this is, there's basically two configurations, which we're going to talk about. One is R and one is S. So a chiral carbon can either be R or it can be S. And the way that we do that is that we assign a priority to the various substituents. And then we determine, first thing we're going to do is assign a priority and rank them from highest priority to lowest priority. Then we're going to make sure that the molecule is drawn in the appropriate perspective. So the lowest priority substituent is pointing away from us. And then we're going to look at the three remaining groups and determine their spatial arrangement. And based upon that, we're going to assign it R or we're going to assign it S. And that's basically what, so when you're looking at a molecule say we're looking at this guy. Put a hydroxyl group up. This carbon here is chiral, and we'll be able to assign it a configuration of being R or S. We could draw its enantiomer, and its enantiomer, drawing the enantiomer is really easy. You just draw the exact same molecule, and the chiral carbon, you just reverse whatever it was. So this is pointing towards us, the enantiomer, it'll be pointing away. So we need to learn how to assign priorities, and then we'll look at the spatial arrangement. So there's a scheme called the Kahn-Ingold-Prelog scheme for assigning priorities, and that's what we'll do next. So we find the chiral carbon, and then we assign a priority to the four substituents that are bonded to that carbon. Okay, so the first step in assigning a configuration at the chiral center is to assign a priority to each group according to these rules. What are those rules? That's the first question. So the first rule is easy. You look at the atoms and determine, you rank them basically according to atomic number. So in the example which we just had, we've got 4 atoms bonded to this carbon, so we are going to look at proton, oxygen, carbon, and carbon. And we rank it based upon atomic number. And so if we remember, hydrogen is atomic number is 1. So, and compare that to oxygen and carbon. Oxygen's 8, carbon 6. So poor little hydrogen is going to be 4th. We can tell that right away compared to the other 3. Its atomic number is 1. Our friend deuterium, the isotope of carbon, it's got an atomic number. It's because it's an isotope, we consider that 2, so it'll be higher priority than H. I'll get to that a bit later on. Then we've got carbons and oxygen. So carbon here, oxygen here. So we can immediately say that this oxygen will be first because it's got a larger atomic number than carbon. So, but we can't distinguish between these two yet because they're both carbon atoms. But the hydrogen and the hydroxyl group, we can say the hydroxyl group's first and the hydrogen is second. So purely based on atomic number. So that's the first rule. Let's move on to the next page. Right, so what happens when we've got things that are the same. I guess I have to, I'll redraw this thing. So carbon and carbon. So if you can't tell the difference based upon the first atom, which would be carbon, then you take one step over and see if you can break the tie there. So this carbon here, what is this carbon here bonded to? We don't count this atom over here because they're both got that in common. But this carbon here is bonded to, call this a star. This carbon is bonded to a carbon right here. So it's bonded to a carbon, and it's bonded to the H that we haven't drawn and the other H that we haven't drawn, because this is a CH2, right? So it's bonded to a carbon, an H, and an H. Over here, this carbon, we don't count this one because that's where it came from. It's bonded to carbon, and it's bonded to oxygen. It's actually bonded to oxygen twice, so it would be carbon, oxygen, oxygen. Then what we do is we compare the highest priority atom on one side with the highest priority atom on the other. So this one's highest is a carbon. This one is oxygen. So this carbonyl, this ketone here, this would be 2, and this one over here would be 3rd. So the hydroxyl group would be first. Carbon, which is bonded, double bonded to the oxygens, would be second. The carbon, which is bonded to a carbon and 2 protons, would be third, and this little proton will be last. So if you ever see a double bond, you assume that it's bonded to that thing twice. So this would be carbon, oxygen, and oxygen. So the highest priority of these 3 things is oxygen, oxygen, carbon, if you wanted to draw it in a sequence. So this other example down here, if we're comparing a hydroxyl group to an ether, oxygen is the same in each case. The hydroxyl group here, this oxygen is only bonded to a poor little proton, whereas this oxygen is bonded to a carbon, and the carbon is higher than a proton, so this ether would have a higher priority than this hydroxyl group. So I think the third rule is basically going to describe what we did with my example here. So if you ever have a carbon which is double bonded to something, you assume that there's 2 of those. So this carbon is bonded to oxygen 1, oxygen 2, oxygen 3. This carbon would be bonded to carbon, carbon, carbon. This nitrile would be considered to be bonded to nitrogen, nitrogen, nitrogen when you're assigning a priority. So anytime you see a double bond, you can assume it's bonded to that thing twice. So if you were comparing a ketone versus a carboxylic acid, so the carbon's the same. So both of those are equal. This carbon is bonded to oxygen 1, oxygen 2, carbon. Whereas this carbon down here is bonded to oxygen, 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 1, 2, 3. So if we're going to compare the two, oxygen tied, oxygen tied, oxygen beats carbon. So because it's a higher atomic number. So this would, the carboxylic acid would be a higher priority than a ketone. So that's basically how it works. So you stay on the same carbon until you break the tie. And if it's still tied after that, then you move over to the next atom one further. An example of that would be comparing a carboxylic acid to an ester. So this carbon is...
Pardon me, sorry. Which group do you start with then? Like, where do you start?
Okay, so like in this, an example like this. Okay, so we're gonna draw a chiral compound here.
Is it like the IUPAC rules then, or?
This is part of CH3. Basically this the RNS configuration stuff comes out of like an international body, which is to do this. But so whenever you're naming something, when you come to a chiral carbon, you will name it R or S in the IUPAC rules for naming things.
Oh, so you start from the chiral center when you're naming this then? That's what you're saying?
Well, when you're, no.
I'm just wondering where the starting point is for this rules, because I'm trying to figure it out, but rule number 1, rule number 2, rule number 3, where do you start with the molecule when you're
Okay, okay, that's a good question. So you start at the chiral carbon right here, right?
Okay.
So you start at the chiral carbon and you look at the substituents and you determine whether or not, like, which you assign the priorities, right? Okay. So in the molecule I've drawn here, the chiral carbon, you don't count that because that's what you look at the groups that are bonded to it. So if we were going to assign a configuration, or if we were going to assign a priority to each one of these, we've got 4 different groups, right? We've got a ketone, we've got a carboxylic acid, we've got a methyl group, we've got a proton. So this is carbon, we'll call this A, this is carbon B, this is carbon C, and we got a proton. So carbon, 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 they're all equal. So that means that this proton comes in last, right? Because it's got the lowest atomic number.
Okay, that makes sense.
Okay, then we're looking at the carbon itself. What's this carbon bonded to? Not including the chiral center, but what are the 3 things it's bonded to? It's bonded to a proton, and a proton. This carbon here is bonded to oxygen 1, oxygen 2, oxygen 3. This carbon here is bonded to oxygen 1, oxygen 2, carbon 3. So now if we're comparing those 3 groups to determine which is the next highest priority, this poor methyl group is only bonded to a hydrogen, which is lower than oxygen and oxygen, right? So it comes in 3rd because it's only bonded to a proton. These 2 are still tied. They're each bonded to oxygen. Then you look at the next one, oxygen. Okay, they're still the same. And then you move over to the 3rd one. This oxygen beats this carbon. So this would be 1st, and then this one would be 2nd.
That makes sense. Thank you.
Now, we're going to do something with all of this once we've assigned the configuration to each one. So the first thing we need to be able to do is determine the priorities, like which is highest priority, which is the lowest priority. Then we're going to set them up in a specific way and determine the configuration. So this is just basically an example of what I just said. So I've got 4 groups here, rank them from highest priority to lowest priority. Oh, I guess I can, let's mute this. Okay, so let's see what we got here. So, so A first, B second, third, fourth. So basically going 1, 2, 3, 4. Okay, let's see how this works out here. So compared to last time, the numbers are much more homogeneous, so to speak. Okay, and each one has got its own different. So okay, so that's okay. That's good. Now what am I doing? I'm trying to get my little drawing thing here. Okay, so first things first. First rule is atomic number. Bromine much higher than nitrogen, carbon, or carbon. So A will be first. So remember, it goes carbon, nitrogen, oxygen, 6, 7, 8. Nitrogen is higher than carbon, which is higher than carbon. So B will be second. So majority of the class certainly got those two correct there. So for fragment C, for the nitrile, carbon's bonded to nitrogen, nitrogen, nitrogen. And fragment D, this carbon is bonded to oxygen, hydrogen, hydrogen. So if we compare nitrogen to oxygen, so we're comparing the highest one in each of the remaining things. Oxygen is higher than nitrogen, so D should be third, and the nitrile will be fourth. So correct. So yeah, it was the majority of the class got 1 and 2 correct. It was just the last two, which was the it's this part here. And it's because this carbon's bonded to 3 of the same things, mentally, sometimes it's easier to say, oh, this has got to be higher priority. But no, it's just, there's only 1 oxygen here, but it's got a higher priority than any of those 3 nitrogens. So the D would be the more highest priority. D would be higher priority than C. Good. Okay. Now, what do we do? So we've got, we've assigned a priority to all 4 of our different substituents on the chiral carbon. What we need to do to make sure that the comparison is the same, or the perspective that we're looking at is the same, is we want to put the lowest priority substituent pointing away from us. So in like 90% of the examples we ever do, that'll be the proton because it's the lowest priority. So we always want it pointing away from us. And so once it's pointing away from us, and there's a number of different ways to draw this. I've sort of drawn 4 different sort of perspectives on this, but in each case, the 4 is the dashed line pointing away. So you want the 4, the lowest priority, pointing away from us. That's how this, when we're assigning a configuration at that carbon, that's how this works. So you want the lowest priority item pointing away. And there's some little tricks on how to do that, which we'll get to in a second. Right. So once it's pointing away, you look at the remaining 3 substituents and you say to yourself, if I go from first, second to third, is this counterclockwise or is this clockwise? Is it going 1, 2, 3 in a clockwise fashion? 1, 2, 3 in a clockwise fashion? I guess I need my little laser here. 1, 2, 3 in a clockwise fashion. 1, 2, 3, that's clockwise. Or is it going counterclockwise? 1, 2, 3. So we're only looking at the remaining 3 now. 4, because it's pointing away, we forget about it. So is it clockwise, counterclockwise, or is it clockwise? If it's clockwise, it's R. And so I always think of this as if I'm driving in my car and I want to turn right. I turn my wheel to the right. And this is the R configuration. So right-hand turn, R. So if the 3 remaining substituents are like a right-hand turn going from 1 to 2 to 3, it'll be the R configuration. And if it's a left-hand turn, then it's S. So R, right-hand turn. It's good when things work out that way in life. So that's basically how you would assign a configuration, is that you look at the 3 remaining ones and you make sure that this little 4 is pointing away, right? So in this example here at the top, oxygen's a higher priority than carbon or carbon. So it's 1. Proton is the lowest priority, it's 4. Carbon here is bonded to oxygen, carbon here is bonded to carbon, so this will be 2. So if we're looking at this 1 to 2 to 3, this is a right-hand turn. So this carbon here would be assigned to R configuration. So this would be R. This carbon would be R. Here's a amino acid here. Here's the chiral carbon, because it's got 4 different substituents. It's got a nitrogen, it's got a carbon, carboxylic acid, and an alcohol. So if we're assigning the configurations here, nitrogen's higher than carbon or carbon, so it's 1. Proton is last, so it's 4. This carbon's bonded to 1, 2, 3 oxygens, whereas this carbon's only bonded to 1, so this is 2. And this, so the proton's pointing away, which is what we want. 1, 2, 3. Counterclockwise, so this would be S. Now, what happens when we've drawn something and the proton's pointing towards you? There's 2 things you can do. You can draw the enantiomer and you can try to redraw this in a different perspective. And that can be problematic. Sometimes, well, depends on how, it's easy to make mistakes when you have to redraw something. What I would typically do is that if the lowest priority atom is pointing towards you, I just check what this answer is, 1, 2, 3, and then whatever it is, I do the opposite of it. So if this is a right-hand turn here, R, going from 1 to 2 to 3, because this proton is pointing towards us, I know that it instead of being R, I have to flip it to make it S, because we've got the wrong perspective on the proton. Or you could redraw it. But I think the easiest way is that if you've got the proton pointing towards you, whatever answer you get, you reverse it. So redrawing this molecule, if we wanted to redraw this molecule, it would look like, you have to flip it over 180 degrees. So it would look like this. So now the proton's pointing away, and you'll notice that the oxygen was down here, but if you flip it over 180 degrees, sorry, can you laser again? Oxygen was down here. If you flip it over 180 degrees, it now moves up, goes from there to there. And this methyl group, which was pointing away, is now pointing towards you. So if we were to assign the configuration here, this H is 4th, like it was before. 1, 2, 3. Oxygen's higher than carbon or carbon. This carbon's bonded to a carbon. This carbon's only bonded to protons. So 1, 2, 3. 1, 2, 3. That's counterclockwise, so this would be S. But I had to redraw all this. I could have drawn it wrong. If I just remember that this proton's pointing towards us, which is the wrong, then we just take the answer and reverse it. That's probably the easiest way to do stuff. So once the lowest priority atom is in the background, you just look at the remaining 3 and just determine if it's a right-hand turn or a left-hand turn. And then you can assign that this little carbon here is R, this little carbon here is S, And this little carbon here is S. And then we've assigned the configurations. And now one common question is, does S correlate to plus or does S correlate to minus? And the answer is there is no direct correlation between the two of them. So some R things will be plus, some will be S. Some chiral molecules have multiple chiral centers. So it's, now there was something in chat, but it seems to have disappeared. Chat. Oh, we are running out of time. Okay, sorry. So we'll pick up there on Tuesday, I guess. There's just a little bit to finish off on stereochemistry. I'm gonna put together a little assignment which covers the conformational analysis of alkanes and cycloalkanes. I hope to have that up sometime over the course of the next couple days. But yeah, thanks for reminding me about the time there. Okay. If there's any questions, just hang around or fire off an email. And I hope everyone has a good day.
Thank you.
You bet.